Thank you very much for having me back again, and it's a great pleasure to be here once again. We're going to take a slightly different line of attack today. Rather than looking at conflicts between science and Torah, we're going to use a scientific concept known loosely as chaos theory, and we'll define that very shortly, to ask some very pointed questions about some philosophical ideas within Judaism, otherwise known as the idea of divine providence, and this will lead to a variety of different questions, some of which are very troubling, very difficult questions to deal with. So this is going to start off as kind of fun with a lot of different demonstrations, but it's going to take a slightly different turn, as you'll see later on. Without further ado, this is our sort of strapline for these talks. We've got to learn the science properly, we've got to learn the Torah properly, and this is what we're going to do this evening. I'm going to teach you the science of chaos theory in about 25 minutes, maybe 30 minutes, it depends. Depends on questions. And then we're going to look at the Torah implications of this idea. So let's look at the science. First of all, I'm going to give you an introduction to chaos theory. What is chaos theory? What does it mean? What's it about? The idea of determinism is a very important idea in chaos theory. There's something called dynamical instability, which sounds very impressive. It's actually very simple and very straightforward. That relates to something called the butterfly effect, which you may have heard of. We will venture into trying to work out what the butterfly effect is and what it isn't, and also look at some of the implications of this, and that will lead us into the section on Torah. So an introduction to chaos theory. So chaos is not about, randomness. It's not about things all going wrong and having a messy house or anything like that, or having little children running around. It's about the issue of whether or not it is possible to make accurate, long-term predictions about the behavior of a system. Okay? That system could be pretty much anything. It could be traffic flow, it could be the stock markets, it could be a football match, it could be a lot of different things. Determinism is the philosophical belief that every event or action is the inevitable result of preceding events and actions. Thus, in principle, at least, every event or action can be completely predicted in advance or in retrospect. Now, what does all of this mean? Well, let's look at the idea of determinism. Now, I have with me these two balls. One of them is a sort of red tennis ball, which I'll hold up over here, you can all see, and this is a little bouncy ball, okay? Both of them have been confiscated from the Friedman family playroom. However, I was able to do a little experiment with these balls, and all I did, if you notice, I'm going to drop them on the floor, and as I drop it, it bounces. It bounces at a certain height, okay? And if I drop this one, it's going to bounce on the floor at a slightly higher height, okay? Now, what I did in my office, and I actually did this experiment, I locked the door beforehand, just in case the chairman walked in, right? I had a ruler up along the side of the wall. Okay, here's my ruler, and this is me looking, this is my eye looking side on, and I held the ball at a certain height at the top of this ruler over here, or at different heights along, and I allowed the ball to drop onto the ground, and as it bounced, I sort of looked to see where the apex of that bounce was, the top of that bounce, and I wrote down the result. Okay, and I did it with both of these balls. That was the experiment that I did. And the results that I got were as follows. Okay, so I dropped the balls from a height of 60 centimeters, and the bouncy ball reached a height of 50 centimeters at its apex, and the red tennis ball reached a height of 22 centimeters, and so on and so on, all the way up to 110 centimeters. After that, I kind of got bored, and I gave up the experiment. However, what I then did was plot a graph. Okay, this is a graph of a bouncy ball in blue dots over here, and you can see that my experiment has gone exceedingly well. This graph appears to be a linear relationship between the height dropped, which is along the bottom axis, the x-axis over here. That's always, in science, the x-axis is always the axis that you're varying, that you have control over. And what you're measuring is the y-axis over here, which is the height bounced, okay? And of course, if you look carefully, I can draw a linear fit through those results. Okay? There is one other point, of course, which I can plot on this graph without having to do any experiments at all. Anyone know where that is? 0, 0. Very good. 0, 0. If I put the ball on the ground, it's not going to bounce anywhere. So this line should extend all the way down to 0, 0, which it does. Brilliant. Not only that, but the beauty of science and proper scientific investigation is that I could also extend this line up. So I can assume reasonably that this linear fit continues. Obviously, as I was giving this shear once, and somebody said, well, it's not going to work if you drop it from space. Okay, that's true. Okay, obviously this relies on normal gravity and things like that, but clearly up to any sort of height that a rabbi is able to get to at any given point in his office, I can extend this line up further without having to do any experiments, and I can assume that that line is going to be linear, provided that gravity remains the same, and so on and so forth. Now, when I plotted the red tennis ball, the graph came out like this. Okay, and again I can plot that line all the way down to the bottom over there, and I can extend it all the way up there. Exactly the same thing. Now, the beauty of this experiment is that I can actually plot both graphs on one on top of the other. There you go. There are my two graphs. And from this information, I can tell something very special, which I kind of knew before the experiment, which is that my bouncy ball bounces more than my red tennis ball. Okay? Brilliant. This is the most unbelievable science. This is the science of determinism. I can determine pretty much where the height of these balls are going to go based on this experiment that I've done. Now, I'm a very clever scientist. I'm also a rabbi. And sadly, rabbis don't earn very much money. So I'm going to now use my expertise in balls that bounce, and I'm going to go to one of these places. Now, I didn't know about these places, of course, being a rabbi, but apparently there are these places where you can play this game of roulette, where somebody takes a ball. I'm an expert in balls, right? And you take a ball and you throw the ball onto this wheel that spins around, and you have to guess which number the ball is going to land on. Some of them are red, some of them are black, and you can put money on which number the ball is going to land on. And when the ball lands, if it lands on your number, you win even more money, right? So it's a great way of making money. Now, being an expert in balls, I should be able to play this game brilliantly, right?
Are you any good at statistics?
I'm brilliant at statistics. I'm a scientist.
So don't play roulette.
Sorry? I don't play roulette. Why won't this work? You say this, you're telling me it's not going to work. Why not?
You haven't got control over the wheel.
One at a time, one at a time. Yes.
You haven't got control over the wheel. You have control over the wheel.
Okay, good. That's a good point.
But an additional factor.
One additional factor. What's the additional factor?
Rotation.
This is rotation of the wheel. Very good. Yes.
And the ball.
And the ball. Yes.
Determinism can't predict random events.
Right.
So in other words, you can't predict the future, what might happen to you in 10 minutes' time. But all it can tell you is what the scientific results are of phenomena that are effectively visible.
Okay. So you're saying determinism can't predict random events, but I don't think this is necessarily random. I mean, I can predict in this graph. I can predict where my ball is going to go. That's a system which is deterministic. This system is apparently not deterministic, but it's not because it's not random. It's not because it's random. It's for something else. Probabilistic. What do you mean by that?
The probabilities of them.
Okay, to say that there are different probabilities, but the whole point is that now I'm an expert in ball physics and everything else. Presumably, if I can make enough calculations, if I can analyze that ball, and if I know the rotation of the roulette wheel, surely I should be able to determine where the ball is going to land. It's no different to the system before, it's just a bit more complex, right?
Well, statistically, if you've got large numbers, you could say the potential of it landing in this number is 1. But because you're doing it individually, you can't do that.
What do you mean individually?
36.
You can't predict the next one. At some stage,
Unless there's a magnet underneath.
There's no dependency, there's no there's what happened before is what's going to happen.
Well, there is. We will. There is. It is the same. It's the same physics. It's the same world. It's the same reality. So it will make the same rules apply. The problem is that this
Too
system.
many variations. Too many
Why not?
variations.
You are different. You haven't got a constant. With bouncing the ball,
Right.
you've got on the surface. You've got the force of gravity.
Yes.
Here, you've got the rotating wheel, which
Yes.
may not be rotating at the same speed every time.
Good. Very good. Very good. You said something very important.
Too many variations.
Too many variations. Too many variations. Very good.
Can have enormous consequences.
Excellent. Any other points? Quickly, yeah.
But it can become deterministic if you can take into account all the different features.
Very good. Theoretically, if I was able to work out all of the different variables that I needed to know, so I knew the speed of rotation of this wheel, and I knew not only that, but the friction underneath, because it's going to slow down, of course. It's going to slow down eventually, and it eventually will come to a stop. I also need to know the velocity at which the ball is released, and the angle, and the direction, and everything else. I need to know the properties of the ball. I need to know which number it starts. I need to know a lot of stuff.
If you knew all this,
Theoretically, if I knew all of that stuff, I should be able to determine where the ball is going to end up. But I can't. I can't for two reasons. Number one, it's impossible to know all of the variables that are going to have an effect on this ball. It's impossible. And even if it was possible to know all of the variables that I need to know, there is one factor that you haven't mentioned yet that is going to create a problem. Yes?
Margin of error.
Margin of error. Fantastic. Let's not read that because pictures speak louder than words, graphs even more so. If I published this graph in a scientific journal, or if I tried to publish it, it would get rejected immediately. Because there is one thing missing from this graph, which are the margins of error. Margins of error are calculated statistically, and you can see, for example, this point over here falls under the line, this is slightly over the line, and so on. The margins of error are calculated statistically, and it shows you how much sort of variation there are between results within certain limits, to show you that, in fact, in this particular experiment, the margins of error are fairly small. I can separate these two. If you said to me, I'm going to pick one of these balls at random, and I'm going to drop it from a certain height, and I want you to tell me which ball it is by working out which height it drops. I could do that because you can separate these two things. In medical research, often what they do is they have two groups of patients, one control group and one group that's given a drug, and one's given a placebo, one's given a drug. And if you can separate those two groups with your errors taken into account, then you can say that you're detecting the difference that the drug's making. So this is a very scientific way of doing it. But the problem is, those errors creep in at a very early stage. And in fact, when I was doing that experiment by looking at where the ball was bouncing to, obviously that's not a very accurate way of measuring the apex of a ball. Okay, you could measure it in all sorts of different ways. I could get a laser system or something, or take very high-speed photographs, and whatever I could do it in a much more accurate way. However, I'm never going to get to an infinite level of accuracy. I'm never going to be able to measure it to 100% level of accuracy. And as a result, although in this system, because it's very deterministic, it's a very simple system, those errors are not going to make much difference. Okay? It's not going to make much difference. But in a system like this, which is very complex, with a whole set of different variables that all depend on one another, those tiny errors in measurement are going to manifest themselves in a very large way much later on. Now, I'm going to explain this point about 3 or 4 different times in different ways over the course of the next 20 minutes. So if you didn't get it, let's go on. Let's look at the idea of dynamical instability and the butterfly effect, and we'll explain why this is so important and why this generates the idea of chaos theory. Now, 1961, this is a guy called Edward Lorenz. He was working with a computer model to rerun a weather prediction. Okay? Weather prediction, by the way, is done through computer modeling. So you take measurements of wind speed and airspeed and temperature and pressure and things like that, you put it all into a computer, and you try to work out where the weather systems are moving. So he entered a decimal figure in of 0.506 for a particular measurement instead of the actual figure, which was 0.506127. Anybody who knows anything in mathematics is that, you know, when you're dealing with numbers of that number of decimal places, you know, when you're doing physics experiments and things, you can round things generally to 2 or 3 decimal places, and that's fine, because ultimately we don't tend to measure things that accurately. So it's a nonsense to write so many decimal places. So he put 0.506 instead of 0.506127. Okay? However, what he noticed is that a completely different weather scenario came about from the computer model. And that was very strange, because the difference between these two numbers is infinitesimal. It's tiny. Now, what he realized is that even though that difference is tiny, eventually that difference, just as our errors of measurement will manifest themselves later on. So we won't be able to determine where the ball is going to land on the roulette wheel. So too over here, he realized that that difference, even just taking off those last 3 decimal points, was going to manifest itself later on in that weather system. So he published a paper on this very interesting effect that he had, and in fact, the question that we have to answer is, why did that experiment go differently? Okay? Why should a few decimal places make a difference? And in fact, we're going to simulate exactly why that difference manifests and what it looks like mathematically. Okay? Now, before we do that, because not everybody is a whiz kid in mathematics, I'm going to give you a little crash course in mathematical functions. Okay? Functions are mathematical operators. Okay? What they do is they take a number and they do something to that number. And a particular function will do the same thing to different numbers, whatever number you put in. So here is a function machine. We're going to take any number that we like. Pick any number that you like. That number we're going to call x, because we haven't determined what it is, we just call it x. We're going to stick it into our function machine, and that function will do something to that number, and out will pop another number that we'll call y. Okay? It's as simple as that. So for example, here we go. If I say that I'm going to take a number, times it by 2, right? Just times it by 2. Pick a number and times it by 2. Let's take the number 20, times it by 2, you get 40. Pick the number 30, times it by 2, you get 60, and so on. And you can plot a graph of functions, and this is what the rather boring function y equals 2x would look like on a graph. Okay? And you can pick other functions as well. Now I can minus 10 from my result. So now, if I take 20, 20 times 2 is 40, minus 10 is 30, okay? And so on. Here's another function which has got an x squared in it, so it's not a linear equation, but 2x squared would look like this. Okay? A nice little curve that goes up like that. And so we can do this for all sorts of functions, and here is the square root of x. Okay? Very nice. That's very interesting. However, there you go. So if I take 25, the square root of 25 is 5. Okay? In case you can believe me. However, I'm going to do something slightly different, because that's very interesting if you're studying GCSE mathematics. But we're not studying GCSE mathematics. This is chaos theory. And we need to do something slightly different to simulate what Edward Lorenz was doing with his weather system, because we said that each event is going to have a knock-on effect to the next event, which is why changing that value is going to have an effect later on. So what we're going to do is take our function machine, we can put a number into it, and we're going to get a number out of it, but rather than simply plotting a graph of different numbers that we're putting in, we're going to take the result of this function, right, take that y, ooh, there we go, and put it back into the top of the function machine. Now that's called an iteration. This is called iterated functions. You take the answer and you make the answer the next number that goes back in. Okay? So for example, we're going to take, this is getting a little heavy now, I know, but don't worry, stay with me. Stay awake, you'll see it's beautiful. We're going to take this equation of y equals 2x squared minus 1. Why? Don't tell me, don't ask, it's fine. It's just a really good equation and it works. Okay? We're going to start off first of all with 0.7499. Okay? And we're going to round that number to 0.75. Okay? Why 0.7599? It's Kabbalistic. Okay? Right. Now, just so that I show you I'm not cheating, I'm not doing anything funny, here is the equation. Okay? 0.7499 goes like this. Here's my 0.7499. It goes into where that x is. I'm going to times it by itself. I'm going to make it go x squared times it by 2 and minus 1. Okay, so there it is. And the number that I come out with is that. Okay, if any of you have calculators on your phones, you want to check it, fine by me. I'm then going to take that result and I'm going to put it back into the equation. Okay? And I'm going to keep doing that. There's that result over there. I'm going to keep doing that, put it back into that equation until I get really, really long numbers. And okay, eventually I'm going to plot a graph of all of these numbers. Now, what is this graph going to look like? Anybody know?
It's not going to be linear.
It's not going to be linear. That is definitely true. Any ideas?
Curve down.
No? Sorry?
It's going to be
Going to curve to an
Curve? Really?
No, it's not going to be.
It's irregular.
It's going to be
It's going to be a wiggly line. Okay, this is the 10 meter. This wiggly line is not random. Okay? The word random should be removed from our vocabulary. It's not random, it's completely deterministic. Because if I put the numbers into this equation and I plot the graph again, I'll get exactly the same graph. So I can determine from this equation, by iterating the same number over and over again through that equation, I'll get exactly the same thing. It's chaotic. It's chaotic because there's no pattern to it. Okay? There's no direct pattern to it. It's not predictable. Now what I'm going to do is what Lorentz did. We're going to round this number 0.7499 down to 0.75, or up to 0.751. So here we go. Here's our equation, 0.75, and we're going to put this into our equation again. Okay, we're going to get some slightly more sensible numbers this time. There we go. Ta-da! And what are we going to get this time? Shorter. No, it's going to be the graph is going to go to the same number. I'm doing 50 iterations.
Oh, that's it. Right.
We're going to do another 50 iterations of the same thing. I'm only showing you 3, otherwise we'll get very bored. But what's the graph going to look like? It's going to be another wiggly line. Another wiggly line. Same thing. However, what difference did you notice between the first wiggly line and the second wiggly line? Yeah, that's a hard question to answer because you can't see it.
Bits.
All right.
More pattern, less pattern. Let me show you. Let me show you.
Less pattern.
It is a bit more frequent, you're right, but it's a bit of an illusion. Let me plot the 2 lines together, and then you'll see what I'm talking about. First person who sees it, shout it out. There's some overlap, no?
As you start, it's the same, but the further you progress, the greater the variations become.
Very good. You start off, you can actually, it's very hard to tell because you've got the blue one on top, but there's actually very little difference in the graphs at the beginning, okay? In fact, it's only, you can see just that bit of yellow peeking out over there, right? And a bit of yellow peeking out over there. And only here do we suddenly find those differences become wildly clear. And in fact, these graphs will never come back to the same place again. So the beginning is almost the same. In fact, what you can do is a really clever trick. You can just minus the 2 results from one another, and you end up with this. Okay? So you can see that here, there's very little difference. Obviously, there's a slight difference, but it's imperceptible. So what Lorentz found was when he ran the weather system again, it looked like it was going in the same direction, but eventually it created so much difference over here that the whole weather system changed, okay? Just from that one tiny change. This is why it's impossible to predict where the ball is going to land on the roulette wheel, because a tiny change in measurements, those inaccuracies that we said, it's going to make a huge result later on, a huge difference later on as to where the ball is going to land, where I predict the ball is going to land. Everyone with me? Good. Okay. So, according to Lorentz, when he failed to provide a title for a talk, he was to present at the 139th meeting of the American Association for the Advancement of Science in 1972, his colleague, Philip Merriles, concocted, does the flap of a butterfly's wing in Brazil set off a tornado in Texas? Now, what does this mean? It does not mean that there's a little butterfly flapping around in Brazil and suddenly, boom, there's a tornado in Texas. That's not what it means. What it means is, if I was to clone the world, the universe, let's say, and look at them in 2 different ways, with a butterfly flapping its wings and with a butterfly not flapping its wings, that's equivalent to not rounding up that number and rounding up that number. Okay? Does it mean that perhaps many years down the line, that tiny difference, which is almost insignificant, it's tiny, it's nothing, but yet the flap of that wing creates some difference in the air around the butterfly, which has a knock-on effect, a chain reaction over days, weeks, months, years, that eventually down the line will be the difference between a tornado or not. That was the question.
Saying that the turbulence will magnify to such an extent.
Well, it won't necessarily magnify, but it will create differences in the weather system that could magnify. That eventually that error, or that difference, will magnify over a long period of time. Okay? That is the butterfly effect. So, I'll show this to you in a slightly different way. So, okay, this is kind of what I've said over here. This is why, the bottom paragraph of it, this is why it is impossible, by the way, to accurately predict the weather beyond a certain time. Do you remember that film? Back to the Future 2, right? By the way, that was set in 2015, okay? So I want to know where my hoverboard is, right? So this, in Back to the Future 2, I think he lands in the future, and they're able to predict the weather to within, minutes. Okay, the rain is going to stop, in a couple of minutes. That is nice science fiction, but it's never going to happen because of this problem. You cannot possibly measure all of the variables that you will need to measure in order to predict the weather that accurately. So there will be a myriad of different things that will affect exactly where the weather is going to end up, which is why weather forecasts can start off quite accurate. Okay? They're pretty good at telling you what's going to happen tomorrow, but not so great at telling you what's going to happen in 5 days' time, and even less so in 10 days' time. Okay? And that is because of this. This period over here is stable. You can predict within a certain period of time. But after a while, you're not going to be able to predict because of chaos theory. You won't be able to determine what's going to happen to the weather. Okay? Anyone remember this date?
No hurricane.
Earlier on today, apparently one ran the BBC and said she heard that there was a hurricane on the way. Well, if you're watching, don't worry, there isn't. They haven't said that, actually. The weather will be coming.
Yeah, he hadn't done his homework, has he? I mean, the truth is that they said apparently women haven't phoned in. It was, whatever, there's a whole mice related to it. But as a result of that, we witnessed some rather disturbing scenes. This was Seven Oaks, which unfortunately became Two Oaks. And indeed, the animals escaped as well. But this is because it's very difficult to predict the weather. In fact, in that particular scenario, there were indications that the weather was changing, but they thought that that weather system was going in one direction and we went in a different direction with the rest of the system. So what I'm going to do is show you another example of this, and the reason this is all blank is because I've brought along a little project with me. This is a pendulum. Okay? This is a very deterministic system. Okay? When I swing this pendulum backwards and forwards, there is an equation that will actually predict, where this will swing. It's very, very deterministic. It goes backwards and forwards very nicely. This is a very, very simple system. However, what I'm going to do, I've never done this before, by the way, quite like this. I've never shown the single pendulum. I'm going to take it off like this. I hope this works. I feel like, do you remember Tomorrow's World? Right, it always used to go wrong. Okay, here we go. This is a double pendulum. Okay, so instead of having just one part that comes down, it's got a link here. Okay, it's linked at the bottom here. This is equivalent to having a sort of non-linear equation for your mathematical. It's a complex system, it's like a roulette wheel. And when I swing this pendulum, okay, you can see it behaves in a chaotic way. Now, it's not random, it's chaotic. So you have the single pendulum which we showed before, and that was what we call a linear system, and this double pendulum, which we call a non-linear system, because it has two parts to it. Okay? Now, because I'm a bit of a geek, if you put a little light at the bottom of this pendulum, and do a sort of photography where you can do it over a long period of time, okay, you can get some very beautiful little patterns. Okay? So this is what I did. I put a light at the bottom of it, and you can see these lovely patterns that it makes. If you try to get the pendulum to make the same pattern, it never will. It's impossible. Because again, trying to get this pendulum to create the same result is like trying to run a system that's so complex, it's like trying to predict the roulette wheel. Because I don't know exactly, which angle I held this at or how much force I put on it or anything else. So we'll create all sorts of different patterns as it's going backwards and forwards. Okay?
If you held this in a template at the correct height, exactly, and you moved it automatically, wouldn't it do the same thing?
The slightest difference is going to manifest. Eventually it will look the same. It will start to look the same. But eventually not. Now, what are the implications of this? What are the implications of this? Well, you may have remembered a film from a while ago called Sliding Doors. It was very popular at the time. I'm going to show you a little clip. Sliding Doors is a bit like chaos theory, the butterfly effect. It was a very popular theme in the 90s. There are a number of films that came out, but this is probably the best that illustrates it. And the idea is that if small differences in a physical system will manifest themselves later on without being able to predict what that difference is going to be, then the same thing is true in our lives. Our lives are also simply a complex system which can be thought of as something that is non-deterministic. We don't know what's going to happen later down the line, as somebody mentioned before. Okay? So I can probably predict what's going to happen this evening and the people that I might meet this evening, but I'm not going to be able to predict, all of the different interactions that I'm going to have later on in the future. So let's have a look at a little clip. So, you get the idea? The whole film then diverts into two films, essentially, plotting what happens in the life of this young lady. One when she manages to miss the train because that little child got in her way, and one when she was quicker because the child was pulled out of the way and she was able to pull the doors apart and get the train. That's why it's called sliding doors. And the idea is that her life ended up being dramatically different because of being able to get the train. Now the question is, how many times in our lives do we make decisions, or do we take opportunities or miss opportunities like that? How many different factors are there going on all of the time which will interplay and interact with one another, which will determine where we end up in life and where we go? The choices that we make, I mean, the big choice is obvious. The university we chose to go to, or the area in which we chose to live. But there are small choices as well. We make choices all the time. We make a myriad of choices just by, having a breakfast cereal. Kellogg's Rice Krispies or cornflakes. Which is it going to be today? That's a difference. That's a decision. It's not a particularly interesting decision, but it's still a decision. It still makes a difference. So, how do we plug this in to the idea of divine providence, and where is it going to lead us?